Hey guys, Tim with Little Crow Gunworks. Welcome back to the channel. Today we are going to talk bullet selection. Oh boy, it's another oh boy video. This one, much like the last one, which is not out yet, it's going to be out on Friday. I want the two videos on powder selection. Those really are going to stir the pot, I'm sure, and so is this video. Bullet selection and getting the appropriate bullet for your application is a lot more complicated than simply just going to the store and grabbing a box off the shelf and stuffing it in your brass and pulling the trigger. I wish it was that simple. It's not. So today I'm going to go through some things that you guys should know and be aware of when you're trying to select a bullet. And because this is about precision, we will not be talking about how hunting bullets work. Like, we won't be talking about terminal performance and how hunting bullets work when they hit animals. If you're interested in that, I suggest watching, I believe it's part 2 of our 7mm Showdown series, where I go into that in detail, and that can help you select a hunting bullet. But this series is about precision. We are still going to cover hunting bullets because I know a lot of you are doing this in an effort to make your hunting rifles shoot smaller. But there's some things about how hunting bullets are designed that you need to consider when making your selection. So I'd like to spend a minute talking about kind of how I wrapped up the last video on powder selection, where I was ragging on guys' knee-jerk reaction to, marry themselves to one powder and then test a whole bunch of different bullets in an effort to find something that shoots small, rather than picking the bullet for the job, whatever that job is, and then trying different powders in an effort to get it to shoot as good as possible. And I can't say enough how important that point is. Please start making a good selection for the bullet you want to shoot that is the best fit for the job you're trying to accomplish, and then use different powders to try to make it shoot, not the other way around. Because what you'll figure out by the end of this video, and I'll probably circle back to it, and that you guys aren't realizing, is that provided your barrel and cartridge and whatever can provide the bullet with adequate stability, you can make just about any bullet shoot reasonably small. Now, you have to be realistic about your expectations and what bullet you select, and I'll go into that when we look at the different styles of bullets here. But provided you select a bullet that is known to shoot small, you can make it shoot small. Don't get yourself stuck in the rut where you think, okay, this isn't working for me, I have to change the bullet. Because when you do that, in effect, and you keep the same powder, but you just change the bullet, in effect, all you're doing is really changing the combustion dynamics, the amount of jump, and how that whole relationship works with the rifle and barrel timing. And like, you're kind of just, it's like you got a dartboard, right? You're trying to hit the bullseye on the dartboard, and what you're doing by changing bullet weights is you're grabbing darts of different lengths and sizes and weights, but you're throwing it the same way. You're not changing anything about your procedure or how you're testing. You're just changing the dart itself and hoping that one of them hits the center. Where if you if you have a whole bunch of darts that are all the same, i.e. stop changing the bullet, and then you just change your process, and instead of throwing random darts at the wall, you have a whole bunch of the same dart, and then you kind of strategically carpet bomb the target. Eventually you're going to get somewhere that you want to be. Like how in this series, where I stuck with the same bullet and the same powder, and I tested 48 different combinations of charge weight and seating depth, trying to find the perfect load or the bullseye. By keeping things consistent and only changing a couple variables that have the biggest effect on how it shoots, I was able to get where I wanted to be, where when you're constantly changing bullets, it's as much luck as anything else. And it doesn't mean that, one bullet is necessarily better than another. It's just the powder that you chose to pair it with, you kind of get lucky, I guess is basically what I'm saying. If you're picking one powder and trying a whole bunch of different bullets and you find one that shoots well, it's more luck than anything else. So All right, I think we'll fire up the screen recording here and get going. 3, 2, 1, and we're live. All right, so remember our Pareto distribution here. We already settled on the 308 Winchester, and in the last 2 videos we went over powder selection and showed you guys how to choose an optimal powder for your application, which has the second greatest magnitude of effect. Now we're on to bullets. So we're going to start by talking about kind of how bullets fly and how they stabilize, and then we'll go into the different factors that contribute to how well they can shoot and the different things that affect their precision potential. So, what is this? This is an artillery shell, but it was something I was able to pillage from online that gives me a good visual aid to describe how this works to you guys. So, when you have a projectile that's this rudimentary shape, you know, the shape of the types of bullets we're trying to shoot. When bullets are in supersonic flight, in order to be stable, they need to be spun, much like when you throw a football. If you just grab it by the end and throw it as hard as you can, it's going to tumble end over end. A bullet's the same way, where if you impart spin on it, it's stable. Well, why is that? Well, when you have this oblong shape and then you push it at tremendous velocity, it doesn't necessarily want to go in a straight line, and it doesn't necessarily want to stay oriented in the direction that you want it to stay oriented. And the reason is that the 2 different forces you have working on the bullet are the center of pressure and the center of gravity. So when a bullet comes out of a barrel at supersonic speed, the center of pressure, meaning all the pressure and force from the drag of going through the air, is out here on the nose. So our center of pressure is toward the front end of the bullet. And typically our center of gravity is somewhere from the midline toward the rear end of the bullet, if it's properly designed. And the key to this relationship working in the bullet staying stable in flight is the center of pressure needs to stay in front of or toward the nose of the center of gravity. But that relationship is very sensitive. So it's not like, okay, we just want to try to get those 2 as far apart as possible or as close together as possible. There's a window where it works really well, and then outside of that window it doesn't work so well. So I'm going to refer to this as we go through and look at the different bullet types, but the general rule is if these are really far apart, meaning like if you have a really long high BC bullet, that encourages these 2 points, center of gravity and center of pressure, to be really far apart, which means that in general, long for caliber bullets, that's another thing I should say. Everything I say in this, it has to be in generalities, otherwise this video is going to be 10 hours long. So everything I say is I'm speaking in generalities. So if you have a long high BC bullet, that means that the center of pressure and center of gravity are going to be far apart naturally, which is why those bullets are harder to keep stable. And I have a couple visual aids here. So this is a 223 Remington steel case, 55 grain complete cartridge. This is a 375 caliber 400 grain monolithic ELR projectile. So when the bullet comes out of the barrel, it'll pitch and yaw a little bit for a certain amount of distance, but it's basically spinning at tremendous RPM trying to stabilize. And when you have a long high BC bullet like this, your center of pressure and center of gravity are really far apart. So when it comes out of the barrel, it's very sensitive to the amount of twist that it has and doesn't necessarily want to be stable right away. Where when you have a shorter, fatter design, the center of pressure and center of gravity are closer together. And they're not too close together, but they're closer together. So that system is a lot easier to stabilize, and it's more rigid in its stability. So it's harder to upset the bullet and make it unstable. And the reason this is relevant is that depending on the bullet design you pick, that is going to affect its inherent precision or its inherent ability to be made to shoot small, where in general, the longer and more radical the design, the harder it is to get it to shoot small. the more compact and simple the design, the easier it is to get it to shoot small. And because of this, like I said, the way we keep these two things in check, keep the center of pressure in front and the center of gravity to the rear, is we impart spin on the bullet. How do we do that? With rifling. So this is just a crude picture I found off the internet that, it's a crude representation of you looking down the barrel of something. That's what you're going to see, is we impart spin on the bullet to keep it stable. How much spin do we need? Well, that varies greatly depending on what you're shooting. So now we're going to pull up the Burger website and we're going to talk about, one, false advertising. Not that Burger is any more guilty of it than anybody else, but also how to calculate what stability you need. And I think this derails more hand loaders than a lot of other things in your quest for getting the smallest shooting rifle you can. I think there's a lot of misconceptions about twist rate and what's required. I think the biggest misconception is that bullet weight has anything to do with twist, or the twist that's required, when in reality it has everything to do with bullet length and nothing to do with bullet weight. So the actual length of the projectile you're firing through the air relative to the twist rate has the biggest effect on anything. And there's also another misconception that people think that if you have inadequate twist to stabilize something, if you just push it faster, shoot it at a higher velocity, that's going to override the fact that you don't have enough twist to make it stable. And that is not accurate at all. Added velocity helps, but the amount that it helps is pretty trivial. And these are just off the cuff numbers, but like, let's say you have a certain system. And let's say the bullet requires an 8 twist to be stable. And you have an 8.5 twist. You say, well, okay, 8.5 is going to be adequate because I'm going to be pushing it 200 feet per second faster than normal. That's not enough. The equivalent to get like a half inch of twist rate is hundreds of feet per second, not 100 or 200 or 50 or whatever. So, a quarter inch of twist is worth way more than any amount of velocity you're going to be able to add to it. So having an adequate twist rate is super important. And what I recommend you guys use is we're going to go into, we're on Burger's website, go up here to resources, and we're going to start by looking at their bullet reference charts. Why are we doing that? Well, because I want to show you an example. So this is where I think a lot of you guys get led astray. And it's that I'm going to cut to the chase and say that you can't trust the recommended twist rates on a box of bullets. They're very generic. And in most cases, they're inadequate. They're going to put the minimum twist they possibly can on there, so that way they can incorporate the most amount of people and try to sell the most bullets. And I'll show you an example and how, even though Burger puts out some of the best information as far as their as far as their ballistic coefficients being accurate, their recommended twist rates, in my opinion, are not. So we'll look at the Burger 7mm 195 grain extreme outer limits. This is a very long 7mm bullet. We see the minimum recommended twist rate is 1 in 9. All right, so 1 in 9. Now we're going to go back up to resources and go to their twist rate stability calculator. This is something that you guys can use to figure out if your bullet's going to be stable or not. You don't have to use a Burger bullet. If you know the ballistic coefficient, the caliber, the weight, and the length, which is the most important, muzzle velocity, twist rate, and then the temperature and altitude you fired it at, you can use this calculator for any bullet. They do have a list of all of their bullets here in this little drop-down menu. So we'll go to the Burger 7mm 195 grain Elite Hunter. So when we select that, it populates everything. G7 ballistic coefficient, caliber, weight, length, and then all we have to input is muzzle velocity and environmental conditions. So most 7mm cartridges aren't going to be able to push that bullet faster than, we'll even give them the benefit of the doubt and say 3150 feet per second. Remember, their recommended twist was 9. So we're already, 3150 is a really high velocity for that bullet, Most cartridges can't push it that fast. But again, we'll give it the benefit of the doubt and say 3150 and 9 twist. Now let's leave this temperature where it is, 59 degrees, altitude 0. So this is essentially at sea level. Then we'll go down here and hit calculate stability. So this is basically the Miller stability formula, and what we're looking for is a SG, that's the score. We're looking for an SG of, it depends on the bullet. According to the Miller stability formula, Berger has found that that SG needs to be at least 1.5 or higher in order to have completely stable flight, where the bullet is not pitching and yawing at all. It's a perfect spiral, and it's flying at full ballistic coefficient value. So in order to get that, this SG needs to be 1.5 or higher. Now, if it's below that, that doesn't mean it's not going to shoot. It just means that there's some amount of pitching and yawing, and that can cause not only your ballistic coefficient to be reduced by a certain amount, but it can cause accuracy issues as well. In my experience, I found that lead core bullets can still group well down to an SG of about 1.2. Although they are pitching and yawing, they can still shoot small down to 1.2 sometimes, depending on the bullet. You start getting under 1.2 and you get keyholing, where basically that center of pressure and center of gravity that we talked about is fighting so much that the bullet's not stable. And you guys have probably seen this, where it'll hit the paper some degree of sideways. Not necessarily 100% sideways. Sometimes it'll go through just a little cockeyed, and what you'll see is you'll see oblong shaped holes in the paper where the hole isn't flawlessly round. You want to see a flawless round hole when it goes through the paper. If it's oblong at all or egg-shaped or whatever, your bullet's not stable. And that's going to cause not only issues at short range and inconsistency problems, but at long range it's going to be an exercise in stupidity. In general, bullets do get more stable as they fly down range, but you don't want to go into a situation where, as it says here in red, your bullet is marginally stable. You don't want to start there. So here we see a prime example of false advertising. In their chart, they say 1 in 9 twist. Well, here we're at 1 in 9 twist, and we're already running it at a velocity that most people won't be able to push it. A more realistic velocity is 3,000 feet per second. And you see that only brought it down to 1.29. So I just got done telling you guys how if you don't have adequate twist and you say, well, I'll just run it faster. Well, look, 9 twists, 3,000 feet per second, 1.29. Even if we add 500 feet per second, it only goes to 1.36. So you're not going to be able to just wave a magic wand and get 500 feet per second. But even if you could, that hardly did anything for the stability. So twist is by far the most important thing in this equation, not velocity. And the reason a lot of times these companies will give generic recommended twist rates is that the environment has a much bigger effect on your stability than velocity. So twist is first, then the environment, meaning temperature and pressure, then velocity. Velocity is a distant third. If we wanted to break it up into 4, it would be twist, then altitude, then temperature, then velocity. And velocity is still a distant last. So we'll put this back down to a realistic velocity, calculate stability. So when you do this, it'll tell you not only what your SG is, or your stability, but it'll tell you, okay, yes, it's marginally stable. Your bullet stability is marginal. You may shoot good groups under these conditions, but the BC of the bullet will not be optimized. And it actually tells you here how much ballistic coefficient you're losing. So by being at 1.29, we're losing about 6% BC. The problem is, it'd be nice if it was a consistent 6%. You could just build that into your ballistic solver if you're shooting long range. But it's not a consistent 6% because it fluctuates with temperature and altitude. We saw that velocity doesn't really affect it. So you think, okay, if I'm in colder temps or hotter temps, that's going to affect my velocity. Yeah, maybe 20, 30, 40 feet per second, but that's not enough to affect your stability. But the temperature is, so we'll do that experiment. So we'll bring it down to 0 degrees, See, it brought our stability, we just went from 59 down to 0. It brought our stability all the way down to 1.14. So now this bullet's probably going to keyhole. And then you bring it up to 100 degrees, 1.39. See how big of an effect that had? Went from 1.14, I think it was 1.29 when we started, and then it went all the way to 1.39. So we had a range of 1.14 to 1.39 just from a 100-degree temperature swing. Remember, 500 feet, adding 500 feet per second only moved at 0.04. And a 100-degree temperature swing moved at 0.25. So see, temperature has a way bigger effect than velocity. Now we'll go back to 59 degrees as a baseline. We're back down to a stability of 1.29. Now we're going to change our altitude. So we started at sea level. What happens when we go up to 10,000 feet? 1.87. Now it's stable. So their recommended twist rate of 1 in 9 only works under certain conditions. If you're up at 10,000 feet, I think you have complete forgiveness with temperature. Yeah, so even if we go down to 0 degrees at 10,000 feet, the bullet's still over 1.5 and is completely stable. And obviously, likewise, at 100 degrees, it's going to be 2.02, plenty stable. So we see that, let's say we're talking average temperature of 50 degrees. Well, let's maybe say 60 degrees. What altitude do we need to be at for this 1 in 9 twist to be adequate? Maybe 4,500 feet. Just about. Close enough. Okay, there we go. So at 3,000 feet per second, 1 in 9 twist, 60-degree ambient air temperature, we need to be at least 4,000 feet in elevation or higher for a 9 twist to be adequate for this Berger 195 grain extreme outer limits to get the full ballistic coefficient, full stability, where the bullet is completely stable in flight and it's not pitching and yawing to some degree. So you see, and this is not a unique situation. Most recommended twist rates are inadequate. I have a tendency to over twist things anyway, just because of that, because I want, under any conditions, basically what I do. So now we see that, okay, advertised recommended twist rates are usually wrong. You should come in here, plug in your situation. I know sometimes the length of the projectile, the length of the bullet you're trying to shoot isn't always that easy to find. Dig and dig and dig and find it. Or if you have some in your hand, get your calipers and measure them. But come in here and look at your individual situation. And what I typically do is I'll say, okay, let's say this is a bullet I want to shoot. I figure out what my minimum velocity would be at the coldest temperatures I would be using it at. So let's say 2,900 feet per second. And then I go, okay, this is let's say I was going to use it for hunting. I wouldn't, but let's say I was. I go, okay, well, I might encounter temperatures as low as 5 degrees Fahrenheit. I'm in central Minnesota. Our elevation is about 1,000 feet. Calculate stability. It says my stability is marginal, stability of 1.18, nowhere close to enough. But then it will also give you a minimum twist recommendation here. So this, under my conditions, recommends a minimum twist rate of 1 and 7.75 inches. So then we put this up to 7.75. That's an oddball twist that you're not really going to find unless you have a cut rifle barrel made. So that has a stability of 1.6. What if we go to an 8 twist? 1.5 exactly. So that would be like the minimum. So for this bullet, in my opinion, an 8 twist is the minimum. Even though we just looked at the reference charts and they say 1 in 9. And again, I'm not trying to pick on Berger. It's just that they happen to have all this data on their website and they have this great calculator that you guys can use. So that's why I picked it. But this is not a unique situation. Most recommended twist rates are wrong. So do your due diligence and get in here and figure this out before you select a barrel twist and or before you select the bullet that you're going to use. Now we'll go into the individual dynamics of each bullet type and talk about what characteristics of each bullet design and type and profile promote stability, and then some of the side effects and negatives maybe of those bullets. And I'm going to do the best I can to do this without notes and just try to hit all the wave tops and hit all the points for each type. So you see a picture, I uploaded a picture. This is a group shot in this series with our 308 and our 175 Sierra Match King. And this is in reference to what I was talking about earlier. This is what you guys want to see in your targets. So whether you're shooting at 100 yards or 300 or 500 or whatever the distance is, and I mentioned this briefly, that a bullet gets more stable as it flies down range. And that's because the rate of travel, like the distance it's traveling and the velocity that it has, decay faster than the rotation. So the RPM hardly changes at all. Like a bullet comes out of a barrel anywhere from 180 to 380,000 RPM. That doesn't really slow down, but the rate of travel, the velocity, certainly does. So the bullet is spinning just as tight no matter how fast it's traveling, so it actually gains stability as it flies down range. So in as little as 100 yards, and certainly farther, you want to see perfect round bullet holes like this. And also the black smudge, you want to look at that too. That black smudge, you want that to be even as well. The more even that is, the more happy your bullet is in flight. It can still have a quasi-round hole or almost perfectly round hole, and you can see that this black smudge might be really thick on one side and really thin on the other side. That bullet's not happy for one reason or another. Even if you have adequate twist for, in theory, even if you go into that Berger calculator and it has adequate twist for what you're trying to do, if the black smudge isn't even, it's not happy about something. Does that mean it's not going to suit your needs? No, but just I'm trying to teach you guys what to look for. All these different factors that you can use and tools you can use to try to figure out if your gun is happy with what you're feeding it. So now we'll go into the first bullet type. So what I did with this is the bullets I'm going to show you guys and discuss are in order of easiest to make shoot small consistently to hardest to make shoot small consistently, i.e. most fussy. So this is a Berger bullet. It doesn't matter that it's a Berger. It could be anything. This is a flat base target bullet that is very short for caliber, has a long bearing surface, and has a tangent. The three different types of ogives are tangent, secant, and hybrid. The tangent is the more traditional, gentle slope, where you see it goes from bearing surface and it gently transitions into a nose, and it's not a radical design. The nose itself is relatively short for the caliber. Flat base. These type of bullets, lead core, so no partitions, no bonding, no nothing, just traditional cup and core, lead core target bullet, right? These, on average, again, speaking in generalities, are the easiest bullets to make shoot small consistently. What's the downside? Well, the BCs are not good, so they're not made for long range, really. You can shoot these accurately out to, say, 300 yards. Past that, there's probably better choices. But the traditional 100 and 200 yard bench rest bullets look a lot like this. Not everybody that shoots short range bench rest uses a flat base. Some of them use boat tails, but they are using, I'll get into it here. So this design is the easiest to make shoot small because it's a lead core and some type of copper alloy jacket. These are, I would say, the least prone to accuracy issues due to barrel fouling or copper fouling. Lead core, thin target jacket are the least prone to that. This next one is basically the same thing, except it has a boat tail. So this is another lead core copper alloy jacket target bullet, much like the last one, except it has a boat tail on it. Still has a long bearing surface, still has a gentle tangent ogive. These are the second easiest type of bullets to get to shoot small, like our 175 grain Sierra Match King that we picked for this series. This design is has a derogatory name for it known as a fat bullet, meaning that it's not sexy. The nose is relatively short. It has really long bearing surface. The BCs are usually very mediocre. They're kind of dumpy as far as a long-range bullet is concerned. Not a real sexy design. However, these are very easy to make shoot small. If you have a gun that you think is questionable and you're not sure if there's something wrong with the barrel, or if you got a bad barrel, or if this, that, and the other thing, and you want to have something to test, try some of these. Whether it's so all the old traditional Sierra Match Kings are this design. Their new generation of Match Kings are very radical, and you'll know by the super high BCs that they have. But the older Match Kings, the traditional ones, are all dumpy like this. They're all fat designs, and they all shoot really small really easily, but the BCs are kind of meh. All of the Hornady hollow point boat tails are this type of a design, with a tangent ogive, real fat design, easy to make shoot small, but not sexy. Berger has quite a few designs like this. I would say less so than other companies, but they're traditional boat tail. So if the bullet is just called a target boat tail, then it's this design. But if it says VLD or hybrid, it's something else that we're going to go into. So for a long range bullet that's easy to make shoot small, but maybe doesn't have the greatest BC, this is your best option. Now we'll go into the hybrid design. So this is, again, another Berger bullet. I'm using all Bergers just because they have nice pictures and representations and high resolution that I can use as visual aids to show you guys. So you see this has a little bit longer boat tail for aerodynamic gain. And then the ogive up here, you see it has a little bit of a longer bearing surface, but then the ogive is what they call a hybrid, where it starts out as a tangent and then transitions to a secant. And the reason they did that is because I just got done saying how tangent ogives are easier to make shoot small. That's why they did it, so that these bullets are unfussy with seating depth, meaning they, on average, they shoot good kind of no matter where you seat them. There can be still sweet spots where it'll shoot better than other seating depths, but in general, these are going to be more forgiving than a radical VLD design, which we'll go into. But then they still wanted the high BC of the VLD design, so they make the nose portion a secant design. So it's secant, tangent, bearing surface, and they call that a hybrid. These are, again, lead core, just like the two previous examples. This is the third easiest design to make shoot small, regardless of the manufacturer. And this would be a good time to bring in, so this is a Berger, I think this is a VLD. This is not my image. This is something I pillaged off the internet again. In the center here, we see a Hornady ELDM. These are extremely similar in design to what I just showed you, to the Berger hybrid, where this has a hybrid nose design where it starts out as tangent and then goes into secant, and then they use a heat-resistant polymer tip to try to gain consistency in length and consistency in nose profile or meeplet, where the traditional hollow points are a little bit tougher to gain consistency at this area, and this is where essentially the most drag is. So it's important that it's consistent, and there's different ways to go about it. And then also on here is the 143 ELDX, and we see that the ELDX is promoted as a hunting bullet. In my opinion, it's mediocre at that job. I think it's adequate for deer as long as the muzzle velocity isn't too high. Like I said, I don't want to go into this for hunting purposes, but we see really the only difference between this is the difference in jacket thickness, where the ELDX has a thicker jacket that gets thicker as it goes down toward the base. And then there's a little teeny retention rib here to try to help keep the core from puking out of the jacket when it's mushrooming. But other than that, there's no difference between it and the ELDM. This has a consistent jacket thickness for the whole length of the bearing surface, which helps promote precision. Just like these other Berger bullets, they are the same way, as you can see, as evidenced by the VLD cross-section here. Notice that the bearing surface, the part that actually touches the barrel, notice the thickness is identical all the way for the length of the bearing surface, which means the engraving force and everything about it, just it's really happy. And we're gonna, as we get into the hunting bullets, you're gonna see how that changes and how that causes traditional hunting type bullets to be more fussy. We can see that a little bit on the ELDX here, how the bearing surface goes from here to here, but we see the jacket gets thicker as we go down, and they do that in an effort to, they want the thing to mushroom, but at some point they want it to stop mushrooming. So they make the jacket thicker and thicker and thicker as you go toward the base to try to keep it from rolling back on itself, because the jacket, under the heat and pressure that you're subjecting it to when it hits something, the jacket at that point is the strongest part of the bullet. The lead is almost in liquid state, so that's very malleable and will go wherever and kind of splatter all over the place, but the jacket is the strongest part, so they make it thicker and thicker to try to keep it from mushrooming all the way till where it turns itself inside out and fails. What's our next example? Okay, here's our VLD. So on this last slide, we were talking about hybrid design of the ELDM and ELDX. These are very easy to make shoot small. Now we have the VLD design. These are traditionally very fussy. They can be made to shoot super small. There's a lot of different bullets that are designed this way, not just Bergers. Like the Hornady SSTs are like this, where they have some semblance of a boat tail, longer bearing surface, but then it's an abrupt transition from bearing surface to sharp secant ogive, where there's almost like you can almost feel the shoulder and the ridge where it goes from this to this, and there's like no transition there. Again, these types of bullets can shoot very well. They do have consistent jacket thickness all along the length of the bearing surface. However, because of that sharp transition, they are super jump sensitive, meaning that there's going to be little teeny windows where they're going to shoot lights out. And then outside of that, they're kind of going to shoot like shit. So these are really fussy, which is why, because people were having trouble with them, that's why Berger started putting most of their effort into hybrid designs. And they basically aren't making any new designs with this VLD profile. They've kind of abandoned it. So the bullets that they have in existence that are a VLD design, they still make. You can still buy them, but they're not coming out with any new ones because they're a pain in the ass. So now everything they come out with now is a hybrid design, because it's easier to make those shoot. And now I think we're going into the traditional hunting bullets. This is an image again that I pillaged off the internet with a cross-sectioned Hornady CX bullet, which would be very similar to any of the Barnes bullets, any of the Barnes tipped bullets. The Barnes traditional X bullets are the same, they just don't have a plastic tip to help initiate expansion. These are, I don't want to say they're a hybrid design, they're kind of close to it, but they're also kind of close to a VLD too. They're kind of in between, where you have a long, very long bearing surface and then some relief grooves to try to reduce pressure and give the material that's swaging somewhere to go. But then the transition here is pretty abrupt. So these have fairly uniform engraving force, higher than a lead core bullet, so these take more force to swage down the barrel, which is why you'll traditionally hit pressure at lower velocity with this design than you will a lead core bullet, because these bullets don't want to swage, which we'll go into shortly here. But these can be made to shoot really well. They can be sensitive. These are going to be more prone to fouling, like having accuracy issues due to fouling of the barrel because of the amount, the alloy that they have to use. They have to use a little bit of a softer alloy, so that way the bullet will actually swage, which we'll go into. Where you can use a different alloy with a target bullet, because the core is so much more malleable that these bullets swage a lot easier, and this jacket is really thin. So because these swage so well in the barrel, you know, copper lead core bullets in general, all of these, that's why I think that's why they're easy to make shoot small. Where these, a lot of people struggle with monos. I don't really. maybe this is a good opportunity to talk about a common myth that you hear online. A lot of guys are saying, because of certain people that have said certain things on other videos, that if you're shooting lead core bullets, like I just showed with all the burgers, you have to scrub the barrel down to bare metal before you start shooting monos, or the monos are going to shoot erratic, and vice versa. I have never seen that. I've never experienced that personally. As an example, in our 7mm Showdown series, with all of the guns, I switched back and forth from lead core to monos to lead core to this to that, and I never cleaned the barrel in between, and I never saw what I would consider erratic fouling issues. The best example is the 7PRC when I shot it at 640 yards. I shot groups with a lead core, 175 grain Hornady ELDX factory ammo, and it shot well. And then I turned around and shot our hand load that was with this 160 grain Hornady CX monolithic. I shot 2 groups at 640 yards. One of them was 3 inches, 3 shot groups. One of them was 3 inches, the other one was 1.5 inches, with no cleaning in between. So maybe you guys are experiencing that. I doubt it. I'm guessing you're experiencing something else that we're going to go into in the series, but I have never seen any issue switching back and forth from one to the other. But what I can say is that traditionally these monos will foul the barrel faster, and you need to clean it more often and do copper remediation more often than a traditional lead core bullet, because again, they have to use a softer alloy that's more likely to deposit itself in the barrel. But again, these monos can be made to shoot really well. It might take a little more work. If you guys have watched any of our videos in the past, you know that I can make those things shoot. Even out to 1,000 yards and beyond, I can make them shoot, but sometimes they take a little more work. This is a Nosler partition. I don't want you guys to feel, those of you guys that like Nosler, I don't want you to feel like I'm picking on them. It's just I'm able to find good images, and they have multiple different bullet designs that are worth talking about. And I know you guys are, some of you guys are doing this for hunting purposes, trying to make your stuff shoot small, so I'm trying to include everybody. Nosler partitions. So these, you would think, because they're similar in design to our target flat base bullet, that these would be easy to make shoot small. And they can be. The trouble is I've found that they're not easy to make shoot small all that consistently. Because, again, our bearing surface here, the part that's being swaged into the barrel, it has constantly varying thicknesses of jacket, and then it has a brace in here, which this part of the bullet does not want to swage at all. And then again, we go back to varying thicknesses of copper jacket. So nothing about this is consistent, which means in general nothing about it is going to be consistent. It might shoot well one day and not the next, and there's too many factors going on here to try to get peak precision out of a bullet design like this. But again, it's a hunting bullet. It's not designed to pound them all in the same hole. It's designed to kill stuff, so which it does a great job of. But trade-offs, you have to sacrifice one thing for the other. You want it to be really good at killing stuff, it's not necessarily all going to put them all in the same hole. And again, we're getting fussier and fussier as we go on here. So I had monos ahead of partitions. I also have monos ahead of AccuBonds. Again, not trying to pick on Nosler. There's other companies that make uniform core bonded bullets that don't have any type of partition or brace in between. We see with this design, your center of gravity is going to be more toward the front, closer to your center of pressure, which for a bullet this long is going to make it fussy. It's going to make it more prone to stability issues. Because you have so little weight in the back here, you have all this really thick jacket and solid base material that's much lighter than the core, and then you see the core is pretty narrow down here, and it gets wider and fatter as we go forward. And again, they did that to try to control expansion so that it doesn't completely turn itself inside out when it hits an animal. But the trade-off is you lose some consistency and precision. Where, I don't want to throw anybody under the bus or pick on anybody in particular, but I talked to a fella that I know is going to see this the other day, and he was talking about the frustrations he's having in trying to make a rifle of his shoot small consistently. And I started helping him try to troubleshoot it, and I asked what bullet he's using, and he said it was an AccuBond, and that was immediately for me was the first red flag, is because I know the way these are designed, you can get them to shoot a small group. In my experience, they don't do it consistently. They're very erratic. They're way more erratic than I would ever tolerate, which is why I don't really use AccuBonds. The only one I've ever used, because I'm a long range guy. You know, if I was only shooting 100, 200, 300 yards, even 400 yards, I would say AccuBonds are just fine. If you're trying to shoot farther than that and be consistent, there's better choices because of this, because it will just throw shots. You'll get a random flyer here and there, and I think it's due to the way they're made and the design, and like there's so much going on here and so much technology and effort that they put into these things to try to get them to hold together. Peak precision isn't in there at the top of their priority list. Getting it to kill stuff and stay together is. So just if you're trying to shoot consistently at long range, there's better choices. And these, I wouldn't say aren't necessarily more prone to fouling than anything else. The alloy that they use, I'm not sure if it's softer or harder, but I would guess these would be less prone to fouling than the monolithics. And then we have the bullet that I seem to be picking on a lot. This is the Swift A-frame. This bullet is really good at killing big stuff really dead really fast. And that's about it. Other than that, this design can cause, and does cause, the biggest inconsistency, erratic, crazy issues I've ever heard of or seen. And the reasons are, I think we're going to need the next slide to explain this properly. So we'll go into these next two slides and we'll come back to the A-frame. This is the end of a barrel. So when we order a barrel, the blank will come, and on the end of it will be stamped the particulars about the barrel. This happens to be a Bartline barrel. This is the serial number. It's a 10 twist. This is a 30 caliber blank. It's stainless steel, has 5R rifling, and the groove is 308, and the land or bore is 299. Typically for 30 caliber, this number will be .300. So this is what I would call a tight barrel, but it's the best image I could find, so you guys could get an idea of what we're talking about here. Now, this is something that I know a lot of people know, but not everybody does. And in order to understand a lot of the things that I said going into this, you have to understand what we're trying to do here when we're shooting a bullet down a barrel. So this is a big misconception, misconstrued thing that people don't understand or get wrong or don't know. So assuming you're looking down that barrel, this is how it really works. So based on the numbers we just saw, 299 bore or 299 lands, 308 groove. So as you look down a barrel, the high parts are the land, or the bore, the actual size of the hole in the barrel is actually 299 or .300 generally for a 30 caliber barrel. And the groove depth from maximum depth to maximum depth is .308. So think about that. If you're shooting 30 caliber bullets, whether it's a 308, 30-06, 300 Magnum, whatever, 30 caliber. If you take calipers and measure the outside diameter of your bullets, they're going to be 308. Well, you're technically trying to blast them at tremendous force down a tube that's actually smaller than the bullet. So this is what I meant when I said that the bullet needs to be swaged. You're blasting it at tremendous pressure down a hole that it doesn't fit down. The only way it fits down it is it has to stretch and get longer and essentially displace and get squeezed, just like in the cartoons, get squeezed and get longer to go down the tube. Well, and then the depth of the groove here, 308, some of the material fills in that void and kind of locks itself into the barrel, and it swages and twists its way down the barrel. That's how the barrel's able to impart spin, is you have to have an interference fit between the bullet and the lands itself. So technically, that's why you can't just drop a bullet down a barrel, because the barrel is actually smaller than the friggin' bullet. So in order for the bullet to be able to swage, the bullet has to be able to stretch and displace. Go back to our Swift A-frame. This bullet does not want to displace. It does not want to swage based on how it's designed. It's constructed so heavily with the partition here, the thickness of the jacket, the fact that not only does this have a partition in it like the Nosler partition, but this is bonded. So not only is there a partition, but it's bonded. So this material does not want to let go of the jacket, where a partition at least has the benefit of the lead material being able to kind of soften and melt and displace and conform and swage to the barrel as it wants, where this stuff does not want to let go of the jacket. So not only does it have this big crossbar in it that is really hard for the barrel to squeeze down, but the lead doesn't want to let go of the jacket either. So this thing is like, it's going down the barrel kicking and screaming the whole way. And in order to be able to make this system even work, they have to use pure copper. They can't use an alloy because the alloys are too hard. So they have to use pure copper because that is actually soft enough that it can actually swage and get this pig down the barrel. The problem with that is copper creates a tremendous amount of fouling. So this bullet is really good at killing big stuff that will eat you in Africa, but it's also really good at creating such bad fouling that if you are able to develop a load that shoots even 1.5 inches, let's say, 3-shot group at 100 yards, which would be pretty damn good for this bullet. Even if you can get it down to 1.5 inches, 1.25 inches, and you have that good load and you just keep shooting rounds down the barrel, just keep shooting 3-shot groups, in fairly short order, your groups are going to go from 1.5 inches to 12-inch groups due to the fouling. I've seen it. Dale's seen it. These bullets are the king of fouling and going from moderately okay to like shotgun pattern. So they require a tremendous amount of maintenance and upkeep and cleaning and whatever just to get them to shoot reasonably small. But again, these are not designed for precision. They are not designed for consistency. They're designed to kill stuff that will eat you very quickly. So this is going back to setting expectations. You have to be realistic about what the goal is and what the objective is and what you're using to get to that goal. Like, don't pick a Swift A-frame if you want to try to shoot little knothole, bug hole groups. Pick the bullet for the job. Have realistic expectations. Try different powders. Make it shoot. So I think that's all I had for slides. Yeah, so I think we covered everything. Covered all the different bullet designs. So I guess, again, going back to these, getting more into the target bullets, which I think, if peak precision is your goal, most of you guys are going to be back here. Just know the difference between the different bullet types that you're shooting or that are potential candidates for your rifle. Know that, the traditional VLDs, the straight VLDs or the straight secant profile are going to be really jump sensitive and really fussy on average, but still can shoot just as small as anything else, but you have to find where it wants to be. And then our hybrid designs like the ELDM, ELDX, and the Burger Hybrid, these are the highest BC for moderate fussiness, I guess I should say. They're fairly easy to make shoot small, and they have really high BCs. And then we have our fat bullets with the straight tangent ogive profile and reasonable length boat tails. These have very mediocre BC, but are super consistent and super easy to make shoot small. I guess that's another thing I should talk about. If you're shooting long range, this is kind of a double-edged sword, where when you shoot long range, part of the contributing factors to how short your rifle will shoot vertically and how consistent your load will be is bullet-to-bullet consistency in ballistic coefficient. Well, that consistency in ballistic coefficient hinges heavily on bullet length. And we're going to go into this more later on in the series. So the length is the biggest driving factor on what the BC is. And when you have this short fat design, these bullets in say a box of 100, these bullets are going to have a much narrower band of length, meaning in a box of 100, all the bullets might be within 10 to 12 thousandths in length because they're a shorter, fatter, simpler design with a tangent ogive. So they're all going to be really consistent. The BC is low, but it'll be consistent. Where a hybrid and a VLD design, they have very long noses, which means it's very hard to get that hollow point bullet to end at a certain fixed point. So while these are going to have higher ballistic coefficients than the short fat design, the variance in length is going to be much greater. Where in a box of bullets that are designed like this, instead of them all being within 10 thousandths, they'll be 4 times that. Maybe more, depending on the manufacturer and whatever. Generally, the more radical the design and the higher the BC and the sexier it is, the more variance you're going to have in length, which means the more variance you're going to have in ballistic coefficient, which means the more variance you're going to have in group height downrange. So it's kind of a catch-22 where you're like, okay, I want to shoot long range, I want the highest BC I can get, but those high BC bullets aren't consistent. So you have to sort them or point them, but you got to measure each one and sort and, figure out what length they are and then clump them into groups, which we'll go into later in the series. So I guess that's it. Just know what you're getting into, know the design of the bullet you're trying to shoot, pick the right tool for the job, and have realistic expectations. Don't pick something that isn't suited for what you're trying to do. And it looks like we're creeping up on an hour here. I got to put a bow on this. So pick the right tool for the job. Pick the bullet that is the best fit for what you're trying to do. Use different powders. Try different seating depths. Try different charge weights, things like that. Force it to shoot. Make it shoot. If you have adequate twist rate and the bullet's stable, there's no reason you can't make it shoot. It's up to you to try different things to figure out how to get it to shoot. I know sometimes that's not the easy button. It's easier to just throw it away and try a different bullet, but that's not the answer. Pick the bullet that is the best fit for your job. Make it shoot. Anyway, that's it for this one. Thanks, guys. Like, subscribe, share with your buddies. I'll see you in the next one.